Welcome to the course on data structures and algorithms. Today we'll start with a binary tree representation into a memory. Basically, as everyone knows about a binary tree data structure. Basically, this is one of the good example of non-linear data structure. In this non-linear data structure, the elements are organized into or in the fashion of parent and child. Moreover, binary tree is a directed graph in which every node has at most two child nodes. Now, in this binary tree representation in a memory, there are two different ways. One is a sequential representation into a memory, and second one is a linked representation in a memory. We will see these two ways in detail. The first way is a sequential representation into a memory. Binary tree elements are stored one after the other array like a fashion. Consider the binary tree shown in the figure followed by its a sequential representation. It's a binary tree in which 20 is at a root, 40 is a left child or left subtree root, and 70 is a right subtree root. Similarly, this is the complete binary tree of this. Now, this binary tree contains 10 nodes. Now, how these 10 nodes of this binary tree are represented into a sequential fashion or into a sequential representation? How do we represent it? If you look at this tree, it is clear that node 70 don't have a left child, node 12 don't have a right child. Similarly, node 18 or the node with a key 18 don't have a right. Basically, I have represented the nodes, they are not part of this binary tree, represented with a green color and dotted lines. Now, in order to do or in order to develop their sequential representation, it is as of this height, or what is height of this particular tree? Let us say this is level 0, level 1, level 2 and level 3. So, there are 4 levels, means it is a binary tree, so that 2 raised to 4 is the maximum number of the nodes to be accommodated into this tree. So that we have taken an array which is of size 16, starting with the 0th index and ending with the 15th. So, initially there is a 20, so directly we are putting it at 0. Then there is a 40, that is a left subtree rooted at 40, so next value is 40. Then right subtree which is rooted at 70, so next value is 70. Then we will go to the left of 40, there is a 10, so we accommodated that 10. Then there is a 12, that 12 is also we accommodated, but this 12, once we move on to add a next element to the 70, there is no left element, and as there is no left element, so after 12 there is a empty space. Then at the next position we included 18, then 22, 26, 24. After 24 there are 3 empty places. 24 there are 3 empty places, so we included that empty places as well. Now, in this fashion, will be representing or will be representing or will be doing a sequential representation of a binary tree. Now, as shown in the earlier figure, sequential representation of a binary tree, there are blank places and that represents a empty nodes. Empty nodes means a nodes without data. From above figure, it is clear that 20 is a root node and whose children present at 1 and 2 place indicates 1 and 2 indices of an array 40 for 40 children are 3 and 4. Based upon this, we will be trying to write some formulation. If root is present at kth node, then its child nodes, they are present at 2k and 2k plus 1 indices in the array. If there is a kth node, we want to understand its parent, then parent probably a parent is present at k by 2th position. There are few notings based upon above description. If there is a complete binary tree, then there will be very less or no empty places in an array representation. And if the tree is left or right associated or left or right skewed tree, then there are many empty places in the array. It is very easy to understand the parent of any node. Basically, these are the three different things that one can note from this sequential representation. Now, let us look at this example, which is a complete binary tree which is rooted at 1, 2, 3, 4, 5, 6 and 8 are the elements. If I try to represent this in terms of a sequential representation, its a sequential representation is 1, 2, 3, 4, 5, 6 and 8, that is 0 through 6 indices. Means all the elements accommodated over here and no blank spaces. Means whatever noting we made earlier, that is, if there is a complete binary tree and there will be a less or no empty places in the array representation. Now, let us take another example where the tree is left associated or a left skewed tree as shown in this figure. 1 is 2, 3, 4. It is a left associated, left skewed tree. Then there are lot many empty places represented or empty nodes represented with E1, E2, E3 up to E11, and they are connected with a dotted lines. Basically, they are not a part of this tree. Now, if you want to do its a sequential representation, that sequential representation, it looks like this. Means there are only 1, 2, 3, 4. There are only 4 nodes. These 4 keys are stored at 4 places, but all other places are empty. It means if you do the sequential representation of left skewed or right skewed tree, then there are many such a wide spaces. Means it is a vestige of memory assigned to that particular array. Now, the same thing is true for right associated tree or right skewed tree as well. Again, this is a binary tree, but it is right associated or right skewed. If you look at its sequential representation, same thing is there. So, the examples we carried out earlier, they both contains many empty places in the array. Means the binary tree which is not a balanced, that creates many blank spaces in the array or in the sequential representation, and absolutely this is a wastage of memory. Now we will look at another representation of a binary tree, and that second representation of a binary tree is a linked representation of a binary tree. Basically, a linked representation, it is as good as the representation we done for a linked list. We know that in case of linked list, there is a node with 3 different fields: a left pointer, right pointer, and a data. Now this representation is given in this figure: data D1 left and right, D2 left and right, D3 left and right, D4 left and right, D5 left and right. Now if we have a tree with a left associated or a right associated, then and we are doing it's a memory representation using a linked representation, then there is less chance of wasting the memory. But in case of array, it's not. Now if it is a complete binary tree, then it requires more amount of the memory, so that this representation is good for left or right associated trees, as well as no wastage of memory. If the tree is balanced, then more extra space is needed to store address of child nodes. So this is means from this we can derive that the sequential representation is having its own advantages and linked representation is also having its own advantages. Means sequential representation is very good for balanced structures, and a linked representation is a good for left skewed or right skewed kind of the trees. Thank you so much. Let me see in the next video.